is essentially probably almost as big as Keyword itself.
Oh,
but it's a nice village. Now, of course, we are just conversating. It's a nice village, quiet, and it's close to Nottingham. So we say Nottingham just because it's 15 minutes by car.
Oh.
Oh,
Yeah, it's a nice place, nice office, nice people, nice colleagues. So happy.
Your city.
good then.
Yeah. Also nice city. It's small enough to not be chaotic, but big enough to have everything you need. So, yeah.
Okay, maybe Mirza, we can start.
Pak Irwan, shall we start?
okay. Shall we start?
Okay, please wait a moment, Pak Irwan.
Yep.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Salam.
Warahmatullahi wabarakatuh.
Good afternoon, ladies and gentlemen. Good afternoon, the Dean of the Faculty of Arts, Science and Technology, Dr. Irwan Melano, the Head of Department Geological Engineering, Dr. Aswan, and Her Excellency Professor Emi Suparka, Dr. Idam. First of all, I would like to thank for your coming in this guest lecture that organized by Geological Engineering, Faculty of Arts, Sciences of Technology, ITB. We really appreciate for your presentation, for your participation for this guest lecture. My name is Mirza. I'm from Geological Engineering, ITB. I will be your moderator for today. Before we start the guest lecture, let me to introduce about this guest lecture that actually this is part of our collaboration between ITB and the University of Oxford that has been started since 2017. And then followed by collaboration with many institutions from UK, including British Geological Survey, University of Birmingham, National Oceanography Center, etc. The topic today's session is about volcanology. Today we will discuss about observing volcanoes from space. Before we start the guest lecture, let me to introduce the invited speaker, Alessandro Novellin, PhD. Please wait a moment. Alessandro Novellin got a bachelor degree from University of Naples, Italy, and then continue at the same university. At 2011, he got master degree, and then finally in 2015, he got PhD from the same university, University of Naples. And then he worked for remote sensing geoscientist at Geomatic Ventures Limited, now TerraMotion Limited. Start from 2017, he moved and working at remote sensing geoscientist at British Geological Survey until now. Okay, ladies and gentlemen, there will be a short and question answer session at the end of the presentation. To ask the question, the audience may use question and answer feature in Zoom or write your question in YouTube comment section during the presentation. The question should be in this following format: name, and then underscore institution or affiliation, underscore question. Due to the limitation of time, we will select the question and continue to the remaining if the time is adequate. So before we start the presentation from invited speaker, I would like to invite Dr. Irwan Melano, the Dean of Faculty of Arts, Sciences and Technology, ITB, to give opening speech. Dr. Irwan Melano, please welcome.
Hello, good afternoon, everyone. I hope you can hear my voice because it is raining outside my office window. So it's
Good.
it is raining, and it is very rare. I mean, it is quite often right now. We have a rain in the afternoon. Maybe to slow down the demonstrations. We have a lot of demonstrations recently. I'm pleased to welcome you today to this very important guest lectures by Alessandro Novellin from British Geological Survey. He will share his experience from small town named Keywords. It is very it's very good to hear that you are doing very important research from very quiet small town, and it's my dream to have be in your place because I used to stay in a very crowded city. So I really hope that someday I can stay writing papers or any academics related things from the small town. And the title of his presentation is very important: Observing Volcanoes from Space. And I think millions of Indonesians live within less than 100 kilometers from active volcanoes. For example, Merapu volcanoes, I think the distance from Yogyakarta and Bantul is less than 100 kilos. And also Guntur volcano, also there is one big town named Garut, very near to Guntur volcano. And predicting when a volcano will erupt is incredibly difficult, even with heavy monitoring. And in Indonesia, we have more 120 active volcanoes. And I think only about 50% of them, I think maybe about 60% of them are monitored. So 40% of them remains unmonitored. And I believe satellite data could help to fill this gap and improve scientific understanding of the complex warning signs a volcano may issue before it erupts. And space-based observations look at least 3 types of data: sulfur dioxide gas emissions, which often increase before a volcano erupts, thermal measurement, and radar data or volcano deformations. I've been working with the volcano deformation for a while by using a GPS and also InShot data. That may they may show us how volcano changing in shape. So I would like to thank Alessandro, who has been working with ITB for quite a while, and especially he's been working with Ibu Emi, Pak Mirzam, Pak Idam. And we really hope this collaboration will continue. And I believe that by participating in this webinar, we are in the right time and also in the right place to understand more about volcanic activity in Indonesia, with our goals to reduce the risk of volcanic eruption in Indonesia. I wish you all a very successful guest lecture. Thank you very much.
Thank you very much, Pak Irwan Melano, for the warm greeting for the audience and also for the presenter. Okay, ladies and gentlemen, without further ado, please welcome Dr. Alessandro Novellin, PhD from British Geological Survey. Alessandro, time is yours.
Okay, thanks. Thanks, everyone. Thanks, Mirzam, for the introduction. I will start sharing the screen. And if you can at least let me know that, can you see it?
Yes.
Yes.
Okay.
Yes.
So I will try to keep the lecture interesting. So of interest for the audience, for Indonesian audience in particular. As you told already, I work at the British Geological Survey. I started around more than 3 years ago. My background is in landslides, studying landslides. So working on Krakatau was, which will be a big chunk of this presentation. It was unexpected, but of course a nice unexpected event for me. And hopefully this will be the start of a long collaboration with ITB. So as you can see, I have also a YouTube channel where I upload presentation, training course about Earth observation for studying and monitoring geological hazard. So in this one, of course, we are targeting volcanoes. I just want to give a framework of an overview. I will start with an overview of why we want to monitor in volcanoes and why Earth observation. Irwan already gave, just summarized the importance of doing this, especially for a country like Indonesia. And of course, there will be half probably of the slide will be just dedicated to the Krakatau volcanic activity during 2018 and 2019. And the work has been essentially funded through 2 NERC grants. You will see the reference below. And one of these grants is, of course, a urgency grant. So soon after the, you know better than me, the unfortunate deadly event of December 2018. As everyone say, we are dealing with risk. So risk is the potential harmful consequences related to an event, in this case, a volcanic event. How we can, so we have to live with risk, okay? How we can assess this risk in volcanic areas, we can do by considering different essentially parameters, taking into account different parameters. So we have, for example, changes in gases. So of course, when magma is coming up from the crust, that it release also in the air elements and volatiles like carbon dioxide, sulfur dioxide. So that is one of the, let's say, marker we can use to monitor volcanic activities. Then we have hydrology, because of course these gases can be released not just in the air, but also in the underground water. We have heat flow, because of course volcanic activity is essentially a compound, is related to transfer of heat from the earth crust. And we have, of course, ground deformation. Ground deformation that is related most of the time with seismicity, because of course the magma is coming through, is creating fracture and is moving through this fracture. So these will all involves inevitably stress changes in the crust. So it's important to keep monitoring, okay, these parameters and understanding when there is an anomalous behavior, okay, because sometimes we can define a pattern different from seismic risk, volcanic risk, and St. Helens example from 40 years ago is a clear demonstration that we can somehow, if not predict the exact day, but have an idea of when things are going wrong. Okay, so satellites help somehow to monitor some of these parameters, so give an idea of if there is something wrong. And why it could be so important, I will tell you now, but you will see later the example. Essentially, they provide info. They are nowadays a free solution. This is the main things. They are free data. Most of them, they are free data. They cover regional scale, national scale. They provide information also at continental scale. So they represent a time-effective and cost-effective solution compared to traditional ground surveys. Okay. In general, so now I will start, we know the issue, what is monitoring these parameters in the volcanoes, but what is Earth observation? So giving the broad meaning of it is essentially anything related to the acquisition of parameters with electromagnetic waves. So we don't touch the object. We could be in space, we can be in the atmosphere, we can be on the ground, but we don't touch the object. That is critical. Now, the parameters we can detect, okay, measure, depend from the interaction we have. So this slide is just essentially, and this will explain some of the findings I will show you later. So how the satellite data, I will be dealing just with satellite data, okay? but this can be applied to any other electromagnetic sensor. So we have passive and active reflector. Passive reflector, they essentially measure what is reflected from the Earth surface, but the source of energy is the sun. I don't know if you can see my cursor, but I will now start using it. While with active reflector, the satellite in this case is its own source of energy, okay? So everything that is reflected back has been generated from the satellite. And you can see that it could be the sun in this example, but what this energy in both cases, passive and active, interact with the Earth surface. When interact, of course, some of this energy can go back, so can be reflected. Some other can be absorbed, so we don't measure anymore, we lost it, okay? But this is, it depends, of course, from the wavelength we are going to use. I will show you later, but it's a minimal part most of the time. And then we have also energy which is naturally emitted from the Earth because of its temperature. So we will be dealing most of the time with both passive and active reflector. They are nowadays equally important. And this is now just to give you an idea of, in terms of physics, this will be the only slide where we will be talking about physics. Then I will, will be just example and application. So for doing Earth observation, it's fundamental using the electromagnetic spectrum. As you can see, you know that, of course, our eyes can capture the energy in the visible, what is called visible band, which is wavelength encompasses wavelength between 0.4 and 0.7 micrometers. But in addition to this, we have a lot more of energy associated to other wavelengths that we cannot see with the eyes, but we can still see through the satellites. Okay, so, and you can see that according to here, there are all the spectral radiance, so the energy associated to the electromagnetic waves that we have at surface. Okay, so you could see that most of them, especially per lower wavelength, is emitted by sun, but also so it's energy emitted by sun and reflected by the Earth. But also we have at high energy what are called the thermal bands, because that is energy wavelength, energy associated to wavelength, which are essentially emitted by the Earth, okay, in this case. And of course, according to the wavelength, we can distinguish different sensors. So we will have multispectral and hyperspectral data. You can see in the middle figure, where essentially cover everything between the visible, near infrared, thermal infrared. We have also LiDAR data. So multi and hyperspectral data are usually adapted for studying length cover changes, and everything that can be then related to volcanic activity, we will see later. LiDAR data, which are operate between the visible and near infrared, which essentially are used for producing digital elevation model. But most of the time they cannot be mounted on satellite, but from highborne instrument, carried instrument. And then we have radar. So radar, as you can see, is far away from the thermal region, and near infrared is in the microwave, so it's everything between 1 millimeter and 1 meter. This is important because you could see the last diagram on at the bottom, the atmosphere transmissivity. This makes a huge difference because essentially, as you can see, when we deal with visible near infrared, we have the problem of the atmosphere transmissivity. Some of this energy is captured from the atmosphere, so or is absorbed or is reflected back. So it means we cannot see, it's like cloud. The example is cloud. If we have clouds, we cannot see what is beneath. So we cannot retrieve anything from the ground surface. So the transmissivity start to get low and low. While this is a problem that microwave don't have. So they can essentially see through the clouds. This is a big difference in a country like UK, for example, where you always have this gray weather most of the time. That makes a massive difference. And also microwave have another benefit. They are active sensor, so they don't rely on the sun's illumination, so they can acquire during nights as well. While with these other, as you can see, near infrared visible, they are essentially energy associated to the sun. So of course, inevitably, we have to have this observation during daylight condition. So we talk about satellite, and now we need to introduce, I will not probably be here without this program. It's called a Copernicus. It's essentially the Earth observation program founded by the European Union, managed by the European Space Agency, and hopefully, it's recorded, this presentation. So I would say big word. It's the largest in human history Earth observation program. There is no comparison with NASA, with anything else. It's the best. And the main benefit is it provides full, free, and open access to data. Okay, we have like a lot of different application already. You can see atmosphere monitoring, marine environment monitoring, land monitoring, climate change, and everything else. So, and essentially, this program has a space component, which are what are called the Sentinel satellites. So these are, at the moment, there are 6 constellations of 2 satellites each. Each of these satellites cover a different portion of the electromagnetic waves, or in any case, deal with a different issue, marine, land, climate, and they provide free data to everyone, okay? So if you type copernicus.hub, you will get access. You just need to register, and then you can download and do whatever you want with this data. These make a huge difference also in terms of volcano monitoring. So now we know the issue, we have the tools, what we can do with these tools. As Irwan was saying, we have to consider that most of the active, we have around probably 1,500 volcanoes worldwide, probably around 50, 100 erupt every year. And of course, some of them, and you know very well, in the Pacific Ring especially, they are in very remote area, inaccessible, so they are not instrumentally monitored. So we don't know what is happening, okay? Or we don't, best case scenario, we don't know, we don't regularly monitor them. So satellite can provide a tool to complement, integrate ground-based observation, or where these are lacking, essentially they can provide observation, which otherwise we will not be looking at. And in particular, Sentinel data providing free data with unprecedented spatial and temporal resolution. I will show you what this does it means. So we can do things that we couldn't do in the past, even if we have satellite, okay, orbiting, even 10 years ago. And additionally, we can, thanks to this satellite, we can now have a long-term and continuous observation. So we can identify, as I told you in one of the first slides, we monitor with volcanoes, gas release, heat flow, ground deformation. We can establish with a long-term baseline against which we can compare any anomalous pattern. So highlight potential unrest period for a volcano. And now let's go to Indonesia. So this is a United States Geological Survey map of the volcano. Of course, Indonesia is essentially an archipelago of more than 10,000 islands. Within this archipelago, we have more than 100 volcanoes, and half of them, as we say, are active. So the problem, another additional problem is, of course, they are scattered around. If you think about west to east surface of Indonesia, extension of Indonesia, we are talking about the same size of US. Okay, so it's a widespread country. So monitor each of these volcanoes scattered around. It's a challenging and costly problem. So satellite can provide a solution to essentially monitor them all. And now I want to, of course, this is the national contest. I want to focus on the Krakatau. So I will give you example of what we could do with satellite data in a real scenario, because of course we have plenty of scientific paper that already prove the importance of using satellite to monitor geohazard like volcanoes. Few are...
hilang ya?
Sorry?
Lost the voice.
Hello? Can I keep going?
Yes, sure.
Still
Yes,
Oh, sorry.
so you can go.
So as I said, we have a lot of publication, but they are theoretical, most of them. This is a nice example of application, okay, of satellite data for a real problem, okay, for a real, in a real case scenario. So I just wanted to provide a fancy old satellite image. This is the oldest I could find for Krakatau. Is dated 1962. The satellite is KH5 Argon, so it's from the US. You should consider at that time, essentially the satellite was taking a picture, so you have a camera, and then it couldn't, of course, it was not the time of internet, so the only way to provide that photo was physically. So there was a canister where the photo, through which the photo was released, and then the US Navy was collecting it once it was landing on the sea. Of course, that was like around 60 years ago, but still looks like ages ago, something inconceivable now for Earth observation scientists. So just to give, and this is how it looks like now. Of course, much better resolution. This is an image from May 2018, so before the arrest happened. You know better than me, but just for the whole audience, the Krakatau is an archipelago of 4 islands, and Anak Krakatau in the middle, surrounded by other islands, Sertung, Panjang, Krakata. This Anak Krakatau emerged during the late 20s or 1920s. We have a lot, more than 50 eruptive periods reported during the Holocene, so during the last 10,000 years. And the risk is high because the population density nearby. Of course, these islands are between Sumatra and Java. We have to consider that within 100 kilometers, you have large cities. First of all, the one on the Java island, West Java. So the exposure is high. So it's one of the area where most have at risk because of volcanic eruption. So, you know, okay, so I can go. And this, just to complete, this is a part of the caldera of the well-known Krakatoa eruption and tsunami generated in 1883. So just to give you a timeline of what happened between 2017 and 2019, so the period through which I will show you some of the findings we had. We have to consider that the Krakatau was quite, let's say, stable for dormant for almost 1 year between 2017 and 2018. And then in June 2018, we have the first sign of eruption started. You could see here the volcano alert level from the Indonesia Volcanology and Geological Disaster Mitigation Center. So we have different level of alert. It's like, sorry, I just need to go back. Different alert level. Of course, green is standard. Everything is safe and fine. And then we progress towards higher warning level. And of course, with warnings, higher warnings mean more restriction. So since June, okay, we start to have some restriction about number of visitors. We should consider that usually 1,000 of tourists go to this place. We say it's probably 2 hours from boat. I was there. So it's around 2 hours, 2 hours and a half from Java. So it's a long way, but still you have a lot of thousands of visitors every year. Of course, from that time you have warning and visitor, and then resident couldn't approach it anymore. You need special permission to go there. So this is a key point, because it means that from that time was dangerous going physically there, and satellite could complement observation that otherwise will not be there available. And then we have the 22nd of December, the collapse, which then of half of the island, which led to tsunami, deadly tsunami. I think more than 400 people died because of this. But still, even after the tsunami, we still have, through March 2019, still the volcano gave sign of unrest. And mainly there were events like fumarole, ashes. Okay, we will see some of these through satellite imagery. So why? So we started, of course, we, especially myself, my role here was, I was involved soon after the collapse of the volcano, so soon after this unfortunate event, because from that moment we essentially, as I told, we need to go back and look at all the signs before and after, see what we can retrieve from satellite data. So until that moment, essentially satellite data played a minor role, okay? But we will see what was the added benefit on using them. This is an example. Of course, it's not just the place that matter, but also the time. Especially the spaceborne EO, Earth observation sector, has grown almost exponentially in terms of data available. This gives you an example. So, for example, we have been working on the period December 2018, March 2018, and we could go back and during this period, we have around more than 200 satellite data between the optical range and the radar range. If that eruption would have had occurred literally 10 years before, we had half of the image available, half of the observation. This makes a huge difference. And these are examples of essentially most of these optical data. They come from these two constellations, the Sentinel one I told you, and the Landsat. A Landsat is a program managed by the US Geological Survey. The data were not free until 2008. You could see this tweet. And you can see that after 2008, so the data were used for free, were available for free, you start have a number of citation and that grew exponentially. Okay, you can see. So people start, and scientists first, start using them. Sentinel doesn't have this issue at all, because they, from the beginning, data starting from 2014 were given for free. And you could see the number here. These are not updated number. I think they're updated to May. And you can still see that more than 300,000 scientists and also public register, and more than 200 of petabytes of data have been downloaded, and more than 24 million of products have been published. Okay, thanks to Sentinel. So this, just to give you the overview of the change it made in our daily life, not just in for studying volcanoes. Okay, So we have this wealth of satellite data. I split here essentially the two domains I told you before. We have the multispectral, so the optical, let's simplify and call optical. We use it for the Krakatau case studies to map water lines, to map tsunami trim lines. Also, I'm not going to show you, but we have also mapped vegetation change, plume elevation, and the erupted material using, you could see the red, green, blue bands, using the infrared in this case. With the radar, we essentially mapped the collapsed area. We extracted the DTM before and after. We will see why was this important. And ground deformation. I put an asterisk here because it's the only things that we didn't do. So of course, I put the citation, but I'm taking information from other group materials. But again, it was possible thanks to satellite data. So I think here I should have, I hope, yeah. So water lines. So what we did is essentially, we say, okay, the volcano collapsed in December. Okay, let's have a look on the water line. So essentially, we started satellite imagery. We go back, you can see, from May 2018, so before the unrest, which started, I told you, 1 month after this. And we start to look at the size of the alien, the shape of the island, and how these could be related to the volcanic activities. So this is, we are going now through the first example. I think this is a video, I hope it will work. So you will see here the time, and the y-axis is the extension of the island. This is the shape. Okay, how we did it, we used what is called, I'm not going in details, but it's called a normalized water differentiation index, NDWI, sorry, normalized difference water index, and essentially it's a simple ratio between bands. We should consider that in this case we use the Sentinel-2 satellite, again, data available for free. It's a satellite which has 13 different bands across the optical range, the infrared. So we take some of these bands, we did a simple ratio across these bands, which could automatically amplify the difference between land and water. And you can see here the huge change of the island. So we have in June, still the island, there is no eruption until June, 18th of June, you can see here. Then you start to have like some change of the island. And I want to show you, this is critical. So you start to see 16th of November, so before 1 month, almost 1 month before the collapse, you could see that the island, the blue line, has expanded towards southwest and south, essentially. We will see later that these are essentially the area where most of the new erupted material was getting in place, okay, was deposited. And then the collapse, and you should consider that this is based on optical data. So you can have, usually this satellite for the Krakatau latitude has a revisiting time of 5 days. The problem being, of course, is optical data. So rely on the sun condition, cloud-free condition, and also plume-free. So there is a gap between November and 23rd of January. So we have like 2 months, 3 months where we don't know what happened. We couldn't see, okay, an optical image, anything. But what we can see in the first image, good image after the collapse, is that the island's shape has completely changed. You could see that we know that, I will show you later, there was a collapse, a failure of the island which generated the tsunami on the west side, but still it has almost fully recovered, regrow, okay, in just few months, and actually in 1 month. And you could see also that the island has started increasing towards east-northeast. So you could see also a big difference on the size of the island in January. And then, soon after, you have like the volcanic activity was still in place, but you don't have any more big lava effusion. But you could see that, indeed, you see that the size of the island stays stable, essentially. But this is an example of how we can analyze, essentially, indirect effect of volcanic activity. So the main being, the extension of the island due to the lava emplacement, and then the rapid regrowth soon after the collapse. A second useful information provided by satellite data was, of course, tsunami trim lines. They are essentially, you can see a sketch here, is essentially the mark left by tsunami. In this case, the 22nd of December tsunami. Of course, they are ideally, we would like to be there and on the ground collect fresh information. But of course, we should consider that sometimes this is not possible because the area, even after the collapse, the volcano was still active, okay? So there were restrictions. So still, satellite data allowed us to see, okay, to virtually visit the place. And we start mapping the effect of the tsunami itself, why could be important, because essentially all the tsunami models are based on observation. So observation about the run-up height and inundation area. Okay, so this is Rakata. If you remember, Rakata is south of Krakatau, southeast expanding Krakatau. So tsunami waves were coming from here, from the north. This is before November. This is January. You could see here all the missing, in this case, tree. Okay, we start mapping the inundated area. It's not a big area. It's less than 1 square kilometers. Most of the of this inundated area is in Sertung, which is, and sorry, but I need to go back. So Sertung is essentially bounding the Krakatau on the west side, and this is essentially because the west side of Krakatau failed on that day. So inevitably was the area most affected. And of course, we can then, having a DTM, we can then derive also for the position on the map of these streamlines, also what is the elevation. So again, these are information that are fundamental to understand, build a tsunami model. And then, of course, from the tsunami model, understanding also how much material slide, which is important because sometimes also Krakatau is the case, involves not just subaerial information, where satellite, of course, can help, but also subaqueous component, okay? But of course, integrating the two is a key, has been a key. Then plume elevation, I have to say that, of course, plume elevation data is usually not done with satellite, okay? We should consider that most of the time it's done with aircrafts or local observation, but still at some point we have like exclusion zones, or even aircraft, civilian aircraft were excluded, so it could have been dangerous. And you could see that this is an image of 8th of January. As I told you, that was the main issue that you have for the optical data. This is a Sentinel-2 optical data. I haven't told you yet, I'm sorry about this. This is a 10-meter resolution image. And of course, sometimes you cannot see what is behind because or you have clouds or you have plume. In this case, we can, of course, still use the data to understand the elevation of the plume. It's just a simple trigonometric, okay, equation where you can essentially you take in account you don't know this age, but you know the shadow length you can measure. Of course, this is user driven, so we have to be careful. We know the sun altitude at that day, in this case is 61 degree, 62 almost, because it's information reported in the satellite data. And of course, then we can derive the elevation of the plume. In this case, we have like almost 4 kilometers. Okay, and this could be important, this plume elevation, to understand also how much material was injected. In this case, this is a number, an estimate given in this paper from Gourier. And yeah, we are talking about 170 kilotons of SO2. And then we go in the radar. So as I told you, radar could be important because it's transparent to clouds and also plume. Okay, so we could see what is below, we could see the surface. This is a good example because luckily we have the same, these are two different satellites of the Sentinel constellation. On the left you have Sentinel-2, on the right Sentinel-1. So the optical on the left, the radar on the right. 16th of November, you could see there is a plume here, some activity going on. The island has been growing on the south part. We will see later how we can be sure of this. And we can see in the corresponding radar image that essentially we don't have any, the disturbance of the plume, it's almost minimal. So what is in this radar image? Irwan spoke before about INSAR. So INSAR, we will go later, is essentially interferometric synthetic aperture radar, that is the acronym, is essentially a technique used to monitor ground deformation from radar image, from the face. Okay, so from the face, we compare image acquired from different image like this, okay, acquired at different time from the same area, and the phase difference will provide us the ground deformation information. Of course, as oversimplified, it's complex. To be honest, it's another world compared to optical data. Even if you have experience with optical data, you will need a completely different training for the radar one. But radar carry not just information about in the microwave, of course, on the phase, okay, but also on the amplitude. And what we are looking here is the amplitude. It's this parameter is called sigma 0. So it's essentially the backscatter signal. We told that the radar is an active sensor, so it creates its own energy. This pulse of energy is going through the earth and then it's coming back. So this is what is coming back. Okay, it's a decimal value because there's a huge range of variation. And when you have a value above 0, it's because more energy is coming back. This is not because the earth is producing its own microwaves, but it's just because the geometry, okay, allow for this signal to be amplified. And of course, and you can see here, the sea is usually, because it's a flat surface most of the time, it's like a mirror, so it's reflecting away the energy and it's darker. And as you can see, this backscatter signal, so sigma 0, it depends from different characteristics, like first the material, then the morphology, and then also the scattering mechanism. And this essentially depends on the wavelengths, because as I told you, we have the radar is still encompass wavelength between 1 millimeter and 1 meter. So there is a huge difference from wavelength to wavelength within this range. But this is just to show you how different can be, and we can carry a lot of information out of it. We will see later. This is not radar. We are still, sorry if I'm jumping back and forward, but I'm just trying to build like a story. This is essentially, again, is a false color image, okay, even if it's a grayscale like before, like the radar I presented before, but it's coming from Sentinel-2. So as I told you, there was from June, okay, material coming out from the volcano. Now I don't want to go in the volcanological section, so I will try to use general terms also because I'm not a volcanologist. I told you that essentially the Sentinel-2 provide bands at different interval. I show you already that essentially what happened here, that most of the energy is emitted by the sun, okay, in the visible and short wave infrared, okay, bands. But if we go further away, essentially most is what is called the thermal infrared, because most of the energy we observe here, okay, is energy emitted, okay. So you have a representation here, is energy essentially the Earth, any object above the zero, absolute zero, emit energy. The problem is that for low temperature, this energy is much lower than the energy coming from the sun, okay. But what happens is for a longer wavelength and for hot bodies, so we're talking hundreds of degrees, the main component of the energy coming to the satellite is emitted from the surface. So we can see hot surface. In this case, I use, we call it hot material index. So we use this band, 11, 12, and divided by 4, just to increase this contrast between different temperatures of the bodies. You could see this is before the activity. 2nd of June. So you could see that the hot is not hot, is a relative, of course. We are talking relative temperature. You could see here that the hottest part of the island before the activity was essentially where we have vegetation. Okay, I'm just going back just to show you, sorry. But you see here, there is a green, nice green area, which then disappeared after the collapse and the eruption. But this was the hottest part because, of course, it was energy reflected back by vegetation, while most of the energy here, also given to the color of the material, was absorbed. Differently from, for example, after June, this is an image from July. You can clearly see the material, as I told you, from the water lines. We knew already that most of the materials, it was coming towards south, okay, south and southwest. So that is where the island was growing. And if we did this for different periods, you could see this is the waterline, shoreline, sorry, I should have called waterline in 15 of May, so much before the activity. And this is November, the green one. You could see that most of we did this exercise of mapping hot material, lava coming out for different periods, at least 10, and they were all going towards south, and they contributed essentially to the expansion of the island. And of course, then we can integrate this information with some empirical relationship. So knowing the type of magma and lava, sorry, we can estimate the temperature and so also have an idea of the volume like these people did. So they estimated a 45 million cubic meter of material coming out during this period. And then, so we have been talking now about the plume elevation, the waterline, the trim lines. We can also have probably the main source of debate, and this is a scientific issue. Now it's no more, we're not talking about monitoring risk and everything, but this is about the scientific debate that essentially was triggered by one thing that people struggle with or have different opinion. Not because they have different expertise or different level of knowledge, it's just because they were using different specific data set. I will go later on this. Essentially, there was a collapse 22nd of December, and then they start, I guess, or people start to wanted to estimate how much of the island collapsed. So you could see here different values These are extract screenshot from different paper, 0.2 cubic kilometers. Then we have these people, they talk about at 0.004. So the main debate and difference and let's say discussion was about the volume of the subaerial failure, okay, associated to the failure, to the landslide. So we have here 0.2, 0.3. They are different estimates. They are all communicated by the same things. They have been looking, apart from Grelli et al., at the same image, okay, which is a Sentinel-1 image, so a radar image like this, okay. So this is the first available image. You probably have seen through probably BBC, also newspaper, Twitter. So this is an image from Sentinel-1. Luckily, it was acquired a few hours after the collapse. I think around 8 hours probably after the collapse. And of course, as I told you, radar, this is the amplitude, so how much energy is coming back. The problem is, of course, radar is not easy to interpret as optical, and radar is mainly used to do INSAR, so to map ground deformation. So we say, okay, we start doing some model with the group from Birmingham, US, Rhode Island University. We start doing some tsunami modeling, but of course the main one information to constrain the tsunami modeling was the trim lines, but also another major input needs to be the volume, okay. For the subaerial volume, of course, we have to start doubting about, okay, probably, of course, looking at this image, I will say the same. This is whole land, okay? So just a minor component of the island. So any of the people cited here, they have done a great job, okay? They couldn't do any better. But this is just because limitation of the data they were using. We start to say, okay, let's look at other data. And so we start looking at aerial photos, high resolution radar imagery. As I told you, we have a wide range of radar observation from 1 millimeter wavelength to 1 meter. So we have different resolution associated to the different radar sensor. This as wavelength used by Sentinel-1 is 5.6 centimeter. Which means a resolution, pixel resolution of around 20 meters on the ground. And we start thinking that probably this might not be land, but might be, for example, volcanic material floating on it, because any tsunami modeling didn't make sense. It needed much more material, okay, to produce such run-up weights, such inundation distance. So luckily we could look at aerial photos acquired the day after, and we start to doubt about, okay, probably is much bigger, the collapsed area. And then we have another satellite sensor. This is not free, I have to say. So we got this from, thanks to a convention agreement between the European Space Agency and the Italian Space Agency. This is an image from Cosmos Skymed, another sensor, which has a better resolution. This is 1 meter. And you can start to clearly see that half of the island was gone. So you could see here some numbers. We are talking about a surface of 1.2 square kilometers, much larger of previous estimate, with a very steep scar surface of 40 degrees on average, with a value of 60, maximum value of 60 degrees. I will start going faster, sorry, but we are almost at the end. And again, we have introducing now the radar image, but radar image are born to do INSAR, so to map ground deformation. That's it. The principle I announced before is this radar emitting a microwave signal, then is coming back and it measures a signal called R1, so which has a phase associated to it. The same signal, the same satellite is coming after, in this case, 12 days for the Krakatau, and is measuring again the phase. If there is any shift in this phase, we have a deformation. Of course, we have to do a lot. There is noise which has to be removed, but what is left is ground deformation. In this case, there is an example of a house, but for the Krakatau is because the island was, and you could see here. So again, if we want to put in the context of volcanoes monitoring, this is information that, of course, you couldn't get in the ground. Probably it was too risky, okay, since June 2008. But we could see that essentially, so what this point represents, this is the vertical component. Red value, okay, it's going down, okay, so it's subsiding. The arrows just show the east and west component. You could see that essentially this part of the island, so the part that then collapsed, the west flank, was already subsiding. This is average motion between January 2018, January 2019, so until the collapse. And you could see in the time, so each of these points has a time series, displacement through time information. We could see that we start to have, since June, so the start of the effusive activity, that we have an acceleration in ground deformation. So this is a motion that is start to accelerate. And so sooner, in correspondence of June, we have an acceleration that then led to the collapse. So INSA could provide a nice way of monitor ground deformation. And then we start also, because of course we need to know the DTM. The problem being here that this is an active volcanic island, which has been collapsed and regrow over the last 100 years several times. Okay, so we need to have the most up-to-date DTM when we want to do, for example, tsunami modeling. So we reconstructed, again, we used this satellite data to reconstruct a DTM. How we did it, because essentially every observation I told of radar observation is associated with a phase measurement from a position. Okay, this position, let's say, is 1 at time 1. Then ideally we would have an observation after 12 days in this case. Ideally it would be from the same place, so from this position 1, but it's never the case. There is always what is called a baseline, so a space shift, which it's bad for INSA, so for measuring ground deformation, because it's an added information that need to be, a noise need to be removed, an error. But it's good for retrieving DTM because it's like stereoscopy. We need to see the same object from 2 different field of view, and we can extract the third information, the elevation. And you could see, yes, indeed, that we have different value for the pre-collapse DTM, the summit of the volcano. Some of them, of course, they rely on 2011, okay, DTM, but we reconstructed from 2 observation, radar observation from April 2018. We generated a DTM with resolution 40 meters with an elevation of around 300 meters, so more or less in line with other observation. You could see that it's blurry, this image, especially on the east side. This is because vegetation is represent a noise for radar imagery, while the flat and dark volcanic areas surface are better surface for detecting radar signal and comparing radar signal at different time. We did the same for August. Of course, in August, the amount of uncertainty was much higher. So this is a DTM we produced, but we didn't use, okay, because the uncertainty, as I told you, is quite big, 40 meters in the vertical dimension. But in any case, we could see, for example, let's say it's good. We have a maximum elevation after the collapse. In this case, August, we did the same exercise. We compared 2 images acquired at different time, close interval in August, soon after the collapse. So the first image soon after available, soon after the collapse. Again, we could see that the elevation was almost 100 meters less. So this information essentially show that we use satellite data, especially when we start to have this dangerous situation to go to Krakatau, to the island. We can provide information about the subaerial volumes associated to the failure, also information about the gassing and plume activity, and also information about coastal change like trim lines and topography change. Information that, of course, have been implemented with work we are doing with ITB, with the University of Birmingham. And to be honest, I have to say that, yeah, at some point, these info, I told you at the beginning, they were like minor, but now they proved to be crucial. So yeah, that was it. I hope you enjoyed, and I was not too long.
Okay, thank you very much for the nice talk, Alessandro. Yeah, so now we can learn how to observe volcano from the space. So before we continue to question and answer session, let me to say a warm greeting to my colleague who just joined, maybe already joined, the Vice Dean, Dr. Agus Muhammad Ramdan. Welcome, Pak Agus. Thank you for your coming.
Thank you, Pak Mejam.
Yeah.
Interesting presentation, Alessandro.
Yeah. Thank you, Pak Agus. Yeah. Bu Rina, also the lecturer of volcanology and geothermal. Thank you for coming. And also Samantha Engwell, yeah, also from British Geological Survey. Thank you, Sam, for your coming. Hello, Sam. Okay, now we will have question and answer session. I've already choose 2 questions from the audience. There are not so many questions. Maybe we can continue the question from the panelists. The first question is from our colleague from Geological Engineering Department. The question is, do you think now is the right time to generate a common public data library for Krakatau? And what type of open data that we should collect?
Okay, thanks for the question. Yeah. In terms of open data from satellite, I think, yes, there is the capability, definitely. Of course, the problem is, so capability to start collecting, okay, information from radar, optical, and start to do a proper monitoring system. But of course, as always, I usually emphasize the good size and of the satellite part. But of course, even now to build a proper monitoring system based on satellite data is challenging, because more than understanding the data, I mean, now we have much better ability to, and some of the time you don't even need training, because this data available online, lessons are available online, programs are freely available. The problem is you need an infrastructure. So you need to create infrastructure that regularly you download the data or visual access the data and you highlight any anomaly. That is the challenge. Can be done, yeah, definitely. But that is, because, for example, if you start downloading the data, we are talking about radar image, they occupy 4 GB each, 8 GB in some cases. So, and they acquire every 12 days for the Krakatau. So even 5 years of data, okay, when we start to have this public record freely available, it means terabyte of data just for storing them. But definitely it's, now is the next step. Now we have for sure the tools to start thinking about a monitoring system. And I think that Krakatau is a good example, definitely, to start, because you have so much activity going on that you can test any model for detecting anomalous behavior. I think, yes, it takes time. Also because you have to think about the long term, because this, for example, this Sentinel mission, which I always refer, started in 2014. So before, you have to collect data from different satellites, which have a worse temporal resolution. So probably every month, a worse spatial resolution, 30 meters. And then you have to think after. So for example, this mission has been funded for 7 years at the moment. At the end of that, we don't know what is happening. So you will probably be dealing with other satellites. So you need always to be, it's a quite, I think for satellite in particular, it's more than research and driven. It's data driven. So it's the satellite that bring you to do more than someone then say, I have this bright idea. That is my thought.
Okay, thank you, Alessandro. Before we continue, actually, I already invite my colleague who also expert in remote sensing for volcanology, Dr. Asep Syekul, but unfortunately, he cannot join for this meeting because he has another meeting. And then the question from my student directly to, he sent me a message. You mentioned about the floating material in Anak Krakatau or maybe the other area, not only in Krakatau. So what is the idea for the next research related to the floating material? So you can
just to so to complete the answer to the previous question, I think it's the time now to start thinking about observatory for Krakatau, starting from Krakatau, and then ideally to expand to all Indonesia, because then would be good to have like a national data set. And Indonesia probably is the best country to start because you can see the benefit of doing it. For the floating material, I think Krakatau start the question of we know radar image, but as I told you, radar still now they are used mostly for doing INSAR to measure ground deformation. People don't use for any other things, or floating, map floating, but it's like a proportion of 90-10% of application. That is floating material. It's Krakatau, good example of stuff we don't know. We don't have a lot of eruption. We started learning together. We don't know what's the backscatter signal. So what's the signal coming from floating material? We know more or less what is the radar signal coming from land, from water, but there are theoretical study of and we can already theoretically model what is the response in floating material in radar imagery, but we don't have a real example real case studies at the moment. So that is, and that could be useful to, let's say, give a final answer to that slide I show you about how much of the island collapsed. Because of course luckily we have another image acquired the day after. Okay, so we can be sure that or let's say we have much more confidence that half of the island collapsed, but we cannot justify at the moment why we see that signal in the 22nd of December. We don't have like a library. We can say, okay, this is floating material. We know that this should be floating material because other case studies prove that is the answer, the signal you get.
Okay. Yeah. Okay. Yeah.
So that is would be a new branch of application for radar data.
Yeah.
And also another good, probably even more than the Krakatau, where luckily for Krakatau we have such a wealth of information. Okay. But it could be also interesting knowing distribution of this floating material from volcanic island for example, navigational purpose, because some of these material can have a floating material extension of cities. So they can and be around for days, weeks, so can create a lot of issue.
I see. Okay, thank you, Alessandro. So that's why you invite my student to join with your research about the floating material. Thank you for the opportunity. Pak Aswan, maybe do you have any question, because you are expert in tsunami and you also have research related to the tsunami from Anak Krakatau collapse 2018.
Thank you, Pak Mirza.
Yeah.
Alessandro, nice presentations. I'm also some research of my research is also about the tsunami deposit because we concern as to the paleo tsunami. I just want to ask you whether you know if about the mechanisms of tsunami if they arrive in the beach. Is it in the case of Krakatau tsunami? Is it also eroded the previous material such as beach sand or even volcanic material that already deposited in the beach? Can you catch my question?
No, to be honest, I will try to answer from my understanding. Of course, I don't have any expertise. Literally, Krakatau was the first from the experience of tsunami. I was on the field. In terms of satellite capability, literally, even with the best satellite resolution, mapping the deposit itself would be unachievable, would be too optimistic, too ambitious. But of course, could be quite easy where you have a huge vegetation, dense vegetation, which has been stripped out from the tsunami. So you can easily map trimlines and having an idea of the inundation area. But in terms of mapping the deposits, no, definitely.
Yeah. So it's been very difficult to identify whether the tsunami already scraped the previous material or not.
Yeah, especially if you have, I told you the marks, you can see the scar, associated to vegetation ripped out. Or for example, for the Palu tsunami, you can clearly see, for example, sheep. There are cases of sheep brought on land. Okay, so but the deposit itself, no, is too. At the moment, even with we have for the Palu tsunami, we have been working with 1 meter resolution data, but still mapping the deposit itself, no.
I see.
Would be useful, of course, but no, we don't have the capability.
I see. Okay.
Thank you.
Okay, thank you, Pak Aswan. Yeah, because from the Pak Aswan result, he found that the tsunami tsunami deposit they found just above the soil, without previous tsunami material. Very different, but what we found in the Sebesi and Sebuku. Maybe Sam, you still remember in Sebesi and Sebuku we found several deposit from tsunami, not directly just above the soil.
Because, for example, talking about the Krakatau, talking with you and people from Indonesia, we have been told that we could see some of these effect and deposits, tsunami deposit, also on Java and Sumatra. But for example, in very few cases, we could map from satellite, even if we know there was something there. There was the tsunami wave struck, but still we couldn't see the effect from satellite imagery. But the good things is you can have straight access, see, because of course, think about our situation from the UK. Even if we work through a urgency grant, still to go to Indonesia, it took a few months. Okay. So you lost in this time the fresh sign and satellite data. You can still map as soon as you have a good image. Or having an idea of where you expect to map tsunami deposit.
Okay, Pak Aswan, is that enough, Pak Aswan?
May I ask one question more?
Yes, of course, Pak Aswan. Yes.
Okay, thank you, Pak Mirza. Alessandro, I also want to know some report that I found from the literature, from the reference told that there are 3 big waves, 3 high waves during that tsunami. But probably that report is especially for the area in West Java, near Banten round. but I don't know whether in South Sumatra, do you know about that? Maybe is, I think, is it 3 big wave is the same or in all place, in all beach near surrounding the Krakatau island, or what do you know? Maybe I think maybe you know from the satellite, probably in the other place is just 2 big wave or more than 3 waves. I just want to know. Thank you.
Thanks for the question, but unfortunately, Aswan is out of my field of expertise. So, for example, we have a tsunami modeler in BGS at the British Geological Surveys, Dave Tapin. So, he has been working a lot over the last 20 years. So, he can give you more information about it, but mainly it's information based on field survey. To be honest, we are already lucky if we can see the trim lines from satellite data, but it's no, definitely we cannot disentangle different waves, or at least for the Krakatau case. Okay, you have to be on the field.
Okay.
I think it's a good way to have a regional idea of where and plan. For example, it could be good because we use some these satellite imagery to, especially for the Palu, we were there also for the Palu tsunami, to go there and, let's say, target specific area, because also we are talking about also for both Krakatau and Palu, the area involved, the area to survey for tsunami depot was quite big. Okay, so you have short time available, so you have to select specific location. Definitely you can use satellite data to target those locations and say, okay, we will do just this area, that's it. But no, try attempting to distinguish different type of waves, and no. I'm sorry, but no.
Okay. Thank you.
Yeah. Okay, Pak Aswan, thank you. Maybe next time I will introduce to Dev Tapin, because Dev Tapin also involved in this joint research. Yeah, so you can discuss later about the tsunami, Pak Aswan, in the Sunda Strait.
Yeah, the good thing, so I mentioned it's part of 2 grants supported from the UK. It's a multidisciplinary team. So I just told you a component of what we have done, but of course it's probably a minor component, because of course there is Samantha here, there is a volcanological side, a tsunami side, agiochemistry side of the story. But what I can tell is satellite data somehow helped all this branch. So
yeah. Okay, thank you, Alessandro. So, Pak Aswan, at this time we continue to study about the floating material in Sunda Strait, as we discussed about the possibility to find pumice material in the Sunda Strait. Maybe if you have something interesting, maybe you can request maybe to our colleague in UK. Maybe you can propose a new topic related to the Sunda Strait area, Pak Aswan.
Okay, thank you. I know that, Mirza.
Yeah, we are very welcome, Pak Aswan.
Thank you.
Definitely, we just started, but it's the good things is an area underexplored. I don't know if it's because it's challenging or because nobody thought about it, and but definitely, as I told you, sometimes data-driven science is stuff that we can do just because we have now the observation more than the intuition. So yeah, hopefully I can have like another presentation just on floating material.
Okay, thank you, Alessandro. Shall we continue, Pak Aswan, with the next question?
Yeah.
Alessandro?
Please.
Yeah.
Thank you.
Okay, Alessandro, the next question is from our student, Uut. So we just want to know and to make sure maybe what is the implication if we can identify the floating material from satellite image. Maybe any specific target from your research?
I mean, for the research itself would be considering, for example, the huge debate and different conclusion about the subaerial failure yeah, that could be like a good way to say, now that we are, let's say we are able to map this floating material, we can say, okay, these also in this image, we are sure that half of the island was gone. So we can confirm our findings. We, of course, we are confident about this because we have other observation. And also we have, I didn't mention, but we have also groundwater seismic survey, so bathymetric survey. So we know the whole picture, okay? But in terms of the general benefit would be probably, of course, for all volcano observatories, because some of these volcanic islands are in the middle of nowhere and probably they are not regularly monitored. So it could be a good, some are submarine, so you don't even see. And another, and also a societal impact in terms of navigation, because I think navigation it's hugely affected, disturbed by presence of this floating pumice deposit, which can have extension of hundreds of square kilometers, like in the Tonga on August 2019. So could be a disruption for that, the shipping industry, fisheries.
Yeah.
So I would say more than the volcanological implication, which is still important, but probably this societal impact.
Yeah. I think this is very interesting. Once we found the floating material, maybe we should change about what we are thinking about the eruption dynamic of the Anak Krakatau during that eruption, I think.
That is another
Yeah.
Also because there are eruptions which start submarine, so and then they emerge this island.
Yeah.
So.
Okay, thank you, Alessandro. Any question from the others? Maybe Bu Emi, maybe any question? Bu Emi, Bu Rina? Pak Idam? Oh, Bu Emi.
No.
Please.
Well, no. I don't. Well, actually, I'm interested, but I'm not familiar with Krakatau, actually. I mean, I've never seriously involving in the research about Krakatau, but one thing that I'm very happy that the data from this method will completing the catalog of Krakatau. That's one thing that
definitely. And also,
I'm imagining. Pardon?
Yes, this information you can also go backwards. So the good thing is you can go retrospective study. So there is probably things that we haven't captured, but still you can go back in time, downloading the available image and study them.
I see. Yeah.
So
that's all. Thank you.
Thank you, Bu Emi. So at this time, I think in the case of Anak Krakatau, we are very lucky because many researchers join in this research. For example, from ITB, we have grant to study about Anak Krakatau collapse, and then from UK team, we have remote sensing volcanologists, for example, Alessandro, and also Samantha Engwell for eruption dynamic. Maybe you will add some information, Sam, about Krakatau research.
Hi, yeah, thanks for that. So that was a really nice presentation, and I think what it shows and what's touched upon is, and the questions touched upon is that satellite imagery is great, and there's lots of different tools and mechanisms that we can use to monitor volcanoes, but it's really difficult to just use one sort of information stream. So by looking at kind of doing the field work going on there, visiting the volcano, talking to communities around to see what they saw, or their observations of the tsunami, all of that together really helps the our understanding of what happens during these events. So yeah, I think this is great. And so from the other side, we're doing quite a lot of geological analysis, so analyzing the deposits and doing some numerical modeling. So these are things that I think over the next couple of weeks we'll talk a bit more about. So I don't want to give any secrets that, well, there's no secrets, but give too much away now. But happy to answer any other questions as well. Thanks, Mirza.
Yeah, okay, Sam, thank you for additional information. Okay, all the audience, just for your information that now we have collect pumice sample and also sample from the surrounding area from Anak Krakatau. Hopefully we can find something interesting related to the collapse of Anak Krakatau. Alessandro, maybe the last question is from Edo. From Edo. Let me good afternoon, Bapak Ibu dosen. Good afternoon, Alessandro. Glad to have you today. I'm interested in an image in your presentation, but I think I missed your explanation.
I wish.
Can you read the question? Yes? There is
so essentially, Mohammed is interested in an image. I just shared the screen again. Is this one? There is an imagery dated just right after the eruption where the resolution reached 1 meter. He asked if it's easy to get this image. This has been 23rd of December. I mean, I would say yes. We just, as long as you use this image for research, it's called you go through the European Space Agency. It's called a third-party mission site. You need to provide a couple of lines on why you need the image, why it's important, and of course some knowledge, because this data is provided through the European Space Agency, but doesn't belong to it. It is a satellite from the Italian Space Agency. So they have this special agreement, but there should be no issue as long as you use for research. So we, as I told you, I don't know, a lot of people have been working on Krakatau on this event. I haven't seen anybody using it. I don't know why. I'm not special, so I don't have any specific, even being Italian, but yeah, just ask the image, that's it. So it's easy.
Yeah. Okay, Alessandro. Thank you. Any other question maybe from Pak Idam? Any question?
No, thank you.
Oh,
okay.
Yeah. Okay, thank you very much once again, Alessandro, for your nice talk and also for the question and answer session. So, ladies and gentlemen, finally we have finished the guest lecture of the day. We have learned a lot today regarding observing volcanoes from the space. May what we have learned today will be useful for us in the future. Before we close this session, would you please to turn on the camera for the panelists? Maybe we'll take a picture or photo session together. Aiden, would you please to help to take picture?
Yes, sure. Wait a moment. Okay. 1, 2, 3. Okay, once more.
Yeah.
1, 2, 3. Okay, thank you very much.
Thank you, Paida. Yeah. Okay, let me to inform you before we close this session that next week we will have another interesting guest lecture from my colleague, Dr. Martin Zutlezer from University of Tasmania. He will talking about submarine volcano and related processes. Please check the date through the official Instagram of our faculty of Earth Science and Technology, ITB. Once again, thank you, Alessandro, Novellin. Thank you for the audience. Thank you,
Alessandro.
Thank you.
Nice talk.
Next week, stay healthy and next week we can go if you want.
Bye-bye.
Okay, bye.
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 Ya, terima kasih,
Terima kasih,
Bu.
Bu.
Yo.
Silakan, Mas Agus.
Kasih ya
Terima
semuanya.
kasih.
Kasih. Ya.
Sam, thank you for your coming, Sam. Idam, terima
Ya.
kasih ya.
Sama-sama, Mas. Ya.
Oke.
Izin dulu ya, Mas.
Ya, dan ini juga mau ditutup ya. Mbak Hana, terima kasih. Silakan bisa ditutup, Mbak Hana. Terima kasih ini para attendee, para audiens. Sampai ketemu lagi minggu depan.